Alrighty. Happy Independence Day if you're in the US. We're going to continue today, but I'm not going to be here the full time, mostly because I have a headache and I don't want to be streaming right now, but I gave my word to myself that I would stream, so we're streaming. And if you're just tuning in, um, I am on a 28-day journey to revamp my knowledge in deep learning technology, specifically PyTorch, GPU programming, and linear algebra. There'll be a whole slew of videos before this. Um, and you're welcome to join me. We're just kind of going through materials, watching the videos. It's dull if you're not studying yourself or interesting. I don't really teach you anything. It's more of a refresher session or a dedicated time to make it happen that I wouldn't otherwise hold myself accountable to if I didn't say I was going to do it. So here we are. So today we're still in the numerical linear algebra study by Fast AI, and I would like to get into some of the other studies. I'm actually not sure I have enough time because I am definitely rusty on this, and it will definitely hinder me if I want to go into an AI engineering job. Right now, I'm purely data science on the business end, so I kind of take what people have developed and implement experiments with it on customer information and retool systems and things that already exist. So I'm not really in the creation of new things quite yet. That being said, we are going to be working on compressed sensing of CT scans with robust regression broadcasting. The term broadcasting describes how arrays with different shapes are treated during arithmetic operations. The term broadcasting was first used by NumPy, although it's now used by other libraries such as TensorFlow and MATLAB. And the rules vary by the library, as always. According to NumPy, broadcasting provides a means of vectorizing array operations so that looping occurs in C instead of Python. It does this without making needless copies of data and usually leads to efficient algorithm implementations, which makes sense. C is much more efficient than Python in a lot of use cases. That's why a lot of libraries are built from C onto Python. So this too is broadcasted or rather multiplied across these items. Same here, if you have an array, you multiply across M and it gives you this. Then you can again multiply across. We use to add matrices and arrays. If they expand, so they added it right. Now notice what happens if we transpose. Oh, Monday transposing got me so confused because I haven't done it in a decade. So we have this expanded dimensions. And if you take this expanded dimensions array with this one, we get this. It seems to either add or subtract from the top one. When operating on two arrays, NumPy compares their shapes element-wise. It starts with the trailing dimensions and works its way forward. Two dimensions are compatible when they are equal or one of them is 1. Arrays do not need to have the same number of dimensions. For example, if you have a 256 by 256 by 3 array of RGB values. You want to scale each color in the image by different value. You can multiply the image by one-dimensional array with 3 values, lining up the sizes of the trailing axes of these arrays according to the broadcasting rules shows that they are compatible. So 3D array, scale, 3D array. This is the code version. So we have this array, and this array. And we give the shapes. This is array of 4, this is 3 by 4, and this is 2 by 3 by 4. Fascinating. If you add A with phi, will it work? And it does something for sure. A is this when you print it out from that map. They transpose, they change the order, so we went from 2 by 3 by 4 to 4 by 3 by 2. And it now looks like this from that. Sparse matrices, and we're shifting to SciPy. A matrix with lots of zeros is called sparse. Sparse matrices, you can save a lot of memory by only storing the non-zero values. Yeah, I remember this from earlier. So to construct a matrix efficiently, use either doc matrix or little matrix. The little matrix class supports basic slicing and fancy indexing with similar syntax to NumPy arrays. As illustrated below, the CO format may also be used to efficiently construct matrices to perform manipulations such as multiplication or inversion. First, convert the matrix to either CSC or CSR format. For each X-ray, we get a single measurement. We need to construct the original picture just from these measurements. Also, we don't want the patient to experience a ton of radiation, so we are gathering less data than the area of the picture. So this is a flattened image put into like a single whatever they were talking about yesterday, like a single deconstructed image. This is the reconstructed image. In the previous lesson, we used robust PCA for background removal of surveillance video. We saw that it could be written optimization problem. Yeah, I thought that was pretty interesting. Original L2 penalization, L1 penalization, which is fascinating that this is what it does to images. I just never thought of it in this context. Compressed sensing. Okay, so we're going to use generated data today, not real CT scan. There's some interesting NumPy and linear algebra involving generating data. Okay, so we're doing some synthetic data generation. Random state. They have a Gaussian filter. They create a bunch of masks. And they're creating binary corrosions on the image. So they generate it, and this is a generated synthetic brain scan. Looks real to me, but it's not, so what can one do? I don't know much. So this is what it's doing. I have no idea what that is. It's making a grid of some sort. Initiating a random state, and so we get this array. If you combine them, we get this matrix. We half it, multiply it times 2 of the original vector. And I guess they're making an outer mask on top of this based on this calculation. And we get this now. They're not actually explaining in the book why we want this, so I might have to turn on the video. It feels like a bunch of blobs, like I'm not getting why this is related to the brain scans. Oh man, this is definitely not the day to do a video. This is generate projections, but why are we generating a projection? Yeah, let me pull up the video because I'm confused as to what they're trying to accomplish with the CT scan data. Like, what's the point of showing me this? Let's see if we can identify.
All right, I'm gonna go.
Where they talk about this.
Beginning every angle and got all this data that you'd be able to reconstruct the original, but you want to limit how much radiation people are experiencing. And so the idea is that we're kind of getting, like much smaller amount of data and want to reconstruct this picture that includes a larger amount of data. So it's kind of like the opposite of data compression in that you're kind of starting with a smaller amount of data and need to uncompress it to get the full picture. And then it's also you're having to find kind of the meaning of kind of what these measurements, so these would be the measurements from different x-rays shot at different angles and different locations, and then getting back to, okay, what would that mean for the picture? I have questions about kind of the setup. And so this problem, since we're using, we're going to use data that we generate for the problem, like we're going to be building this picture. It's different from a kind of real CT scan in that we first will have to make our data, then get what the measurements would be, and then we're seeing if we can reconstruct the original just from these measurements. So I'm going to show some pictures, but kind of what it'll look like is that an X-ray shot at a particular angle and a particular location, you're just going to get a single number from that. So here we have a line intersecting with our picture, and that would result in just one number. So kind of one pixel in this left-hand side of our measurements. And then this is a kind of brief review. So from the background removal lesson, that was background removal using robust PCA. It was written as this optimization problem. And do you remember what's special about the L1 norm? Shout it out. It shrinks things to zero, resulting in a sparse solution, right? So it induces sparsity because, it's kind of pushing many of the coefficients to zero. And so you'll notice this picture that we'll be trying to construct is sparse. So we'll be using the L1 norm today. Okay, so the first part of this is just generating the data, and I think this uses some interesting NumPy methods that some of them I hadn't even seen before. So I think it's an interesting process. Again, if you were really working with CT scans, you're not building your own fake data set. And so here we're choosing 128 for the dimension. So this is 128 by 128. And I'm going to kind of walk through what this code is doing. So this is the whole method for generating synthetic data. This will return kind of one square like this, but we'll walk through that more slowly. And to walk through it, I'm going to go through kind of a smaller example of just creating an 8x8 picture that has five points. And we'll see what the points mean in a moment. But that'll give you kind of the density of the data set of those white circles. So there's a NumPy method called ogrid that returns something as a column and as a row. And so here we're getting the numbers 0 to 7 as a column and as a row back. And then this is actually going to be very handy in a moment. We're going to use broadcasting with this. So we want to end up getting something that's 8 by 8. So we're kind of getting this row and column, and we can do some operations. And together with broadcasting, that's going to go from having something that is 8 by 1 and 1 by 8 to something that's 8 by 8. It's kind of a handy trick. And so this is basically kind of like the equation for a circle. We're saying x minus a center point squared plus y minus a center point squared, and we get. And then kind of combining that with broadcasting. So the x part of the equation is still just going to be this 8x1 column. The y part is this 1x8 row. And when we add those together, we get an 8x8 grid. And this kind of has a density of being 0 at the center and then getting larger as you go further away, since we're using the circular equation. Any questions about this? Jeremy?
Can you show us what x plus y looks like?
Oh, yes, that's a great idea. And here, since 0 is the first entry of both, you can kind of see the original x in the first column and the original y here. And so now we're constructing something called mask outer. And basically that's because we're just going to be kind of interested in this center, in the, kind of the center of our picture. And I think this is kind of fitting with the idea of, if you thought about doing a CT scan of someone's, someone's torso, that you're kind of getting this like circular cross section is what we're getting here. So we're just adding an inequality. So kind of taking our XY grid and then seeing when it's less than this radius squared, that gives us this outer mask, which is kind of a ball of truths surrounded with false at the border. And this is also important, I should say, I guess, because the X-ray will be coming at different angles. Like this kind of ensures that it's going through the same amount of, person being X-rayed kind of from each angle. The X-ray's traveling a similar distance. So we take that mask. So that's our outer mask. And then we're constructing something called mask, where we just randomly generate some points in a 2D grid. And so that was a parameter earlier, kind of how many points we wanted to generate. In this case, it's 5. So we've still got something 8x8, and it's all zeros with 5 ones. And we can plot what that looks like. So here we're just plotting kind of each point is a pixel, 0 or 1. And we have five white boxes. We'll use a Gaussian filter then to kind of blur that. So that's kind of going around these places, but making it a bit more kind of continuous. And this is, some of this is, this is specific to kind of like we're trying to get these like globby looking shapes in our data. Here we combine seeing when, so now we've kind of on this Gaussian filter version, we're just going to take the parts of that are greater than the mean for it. And then also when those points lie inside that inner circle. And so that's what this is. And then actually I should maybe pull up ND image. Oh, I'll come back to that in a moment. We're kind of using this additional library. Here is where we get this binary erosion feature from. And this is just picking out the middle. So kind of this was our whole thing. We wanted to separate that into what was the middle and what was the exterior. And so this is how we make, kind of make those globs that you saw. And this is a more pixelated version since it's just 8x8, whereas our original was much larger. But this, actually, let me scroll back up. So kind of this circular shape, or not circular, globby shape here. That's how we would get kind of the globby shapes here. Jeremy?
Can I say maybe what mentioned that caret sign at the end?
Oh, yes. Yeah, the caret sign is XOR, which is exclusive OR. Actually, first let me just see where ND image. Okay, so that is a SciPy library. I'll go back to that. Yeah, so Jeremy pointed out the binary erosion gives us the inside. Really what we want is what's left over. And so we're taking an exclusive OR with kind of between this picture, the result that's everything, exclusive OR with this interior just leaves us with the exterior. And then I just wanted to pull up, because I think this is an interesting library. We're just using a little bit of functionality from it. But SciPy has an ND image for multidimensional image processing, kind of as a library. So if you're interested in it, I think that would be something to check out with, with different types of filters. Other questions kind of so far what we're doing to create these globs?
Can I have a question about this Gaussian filter? Is this something like the EM model?
Remind me what the EM model is.
So we assume that there are like a few Gaussian distributions, and then we assign probabilities to every pixel that was derived like from white distribution or from black distribution by looking for the maximum likelihood.
I think this is more like putting a Gaussian centered at each point and kind of looking at what shape that creates.
At each point, at each pixel, right?
So we have like the 5 pixels that we've made white, and we kind of like are putting Gaussians centered at each of those and looking at the distribution that creates.
Oh, I see.
Let me pull up the documentation though. Oh, there it goes. Yeah, I guess it is like Jeremy's saying that he thinks it's like a convolution. Yeah, I think that's accurate. Oh. Like what this, actually got me the violet. What this looks like in 1D, or in, I guess kind of in 1D, would be kind of like taking the points you have, and if you put like a Gaussian around each of those,
Mm.
oops, and then you're kind of looking at the method that covers all of these. You kind of hear about this in kernel methods sometimes, kind of like looking at where the data is, and then kind of using Gaussians to construct a distribution kind of based around that data. Yeah, good question. Any other questions? Matthew?
Sorry, can you clarify?
On the Gaussian?
Yeah.
So what that's doing, yes, I think Jeremy pointing out as a convolution is helpful. It's kind of like blurring the points around wherever we have these white pixels. So we were kind of starting with this picture, and so you can think of that as kind of doing this averaging method to kind of even out the squares around this. And so that's why we kind of have it very white in the corner. But if we take a point here and get the average of the stuff around it, that's going to be gray. Whereas a point here, an average of everything around it's still going to be black.
Mm-hmm.
And that's a way that kind of like smooths it out. Oh, you're welcome. Okay. And we can always come back to this later too. So this is, so that's kind of just to getting that that kind of picture with the globs that in the end is going to be what we're trying to recreate. The next step is to generate the projections. And so this will be the kind of the single value that we get from shooting an X-ray at a particular angle through our picture. So again, I'm going to walk through this. And this is something where you don't have to understand every line of the code. This is, okay. But more, I want you to kind of get the idea of like what the steps are. I should also, just while it's on the screen, want to highlight, here we're using sparse.coo matrix in this line for our operator. But yeah, so here we're kind of feeding in what the dimensions we want it to be, and we have L as well as L divided by 7. And again, the idea is that we're using less radiation than kind of, taking it at every single angle and every single location. And so this creates, we'll kind of come back to what this matrix looks like. But we've got a sparse matrix in coordinate format. And then there is a dense method, which converts sparse matrices to dense and is very useful. And that'll be helpful when we're wanting to plot what we're doing. We need to have it dense for creating these images. But the idea is that the first dimension is going to tell you the angle, and we only have L over 7 angles. And then we have L positions. So that's kind of every single pixel height. And then each image is L by L. So we're going to be getting something that's L over 7 by L by L by L. So just to kind of get a feel for this matrix, this is an angle indexed with 3, and we're kind of have it starting from 0, or just at kind of position 0, and then you'll notice the positions moving and basically getting lower each time. So then this is position 1, which is really from this distance almost looks identical, but the line is slightly lower than the previous picture. Can go on 2. And it becomes more obvious if you say go to position 40. So now we can see, like, okay, we've definitely been lowering this angle, kind of keeping the same angle, in this case, the angle with index 3, and going to a different position. So now we're lower, kind of down to 40. And then we can look at other angles at vertical location 40. So now I'm changing the first coordinate to be a 5, and this is a different angle. And actually, let me kind of show, like, if you did 4, 40, that's giving you something in between angles 3 and angle 5. And so what we have is a kind of a matrix that's keeping track of all these different angles and locations. Here we can see this is a completely different angle, the one indexed with number 15, at location 40 still. This is angle angle index was 17 at location 40. So we're kind of getting all these different angles at every possible location, where here the location basically corresponds to the height within the picture. Questions about this? And this is a little bit tricky because projection T is it's a matrix in 4 dimensions, which can be hard to think about. So here we're kind of just looking at these 2-dimensional pictures from it by indexing the first and second dimensions, and then we're seeing everything that's in the third and fourth dimension. Matthew?
Just to recap, what is the projection again? Is that
So the projection, and we'll kind of get to that in a moment. The projection is going to talk about how we're projecting into one dimension, which is weird to think about, but it's going to be kind of taking this, this line at a certain place together with our whole image and just getting a single number from that. Yes. Jim. So that's representing what the CT scan gets, because the CT scan, you've got this. The cross section, 2-dimensional cross section of a person, and you're sending an X-ray at a particular angle. And even though those could be represented as, like a 2D picture of the X-ray, the 2D picture of the cross section of the person, you just get a single number from that, which is like the reading that the CT scan or MRI machine is picking up. So kind of getting that down to a single number. Yeah. So typically, so projections are kind of take something, that goes from a higher dimension to a lower dimension. I think this is somewhat unusual because I feel like people often don't talk about projections into 1D. Any other questions? Okay. So yeah, now I'm just kind of showing you can transpose, X-ray kind of going through these points. We're just going to get a single number from that. Here I've also showed just how much intersection there is. And the idea here is that the X-ray kind of going through different materials of different densities, that's going to affect the reading at the end. So it's got a sense of kind of kind of like the density of what it's passed through based on kind of what the measurement is. And so here I wanted to illustrate that. And so we get this from, so here Proj stores the projection. This is at the very beginning when I showed that little L over 7 by L matrix. This is the readings. And so here, where there was a lot of intersection, like this X-ray was having to pass through a lot of the globules, we get a kind of larger number, 6.4. And then here, we have a line kind of going off through the side part. It's not really passing through much, and we'll get a lower number. That, yeah, just 2.1. So this is kind of how we're capturing information of how much the line has passed through. And then we're also adding, we add some noise to that. So kind of assuming that this would involve some noise in our measurements. And then this is what we're referring to as kind of the projection. This matrix, but that's just all the measurements. So it's a bunch of 1D projections coming from these lines at different angles. Tim?
what's the star Proj shape inside that argument? Why is star there?
That's a good question. So star in Python is used to unpack lists. So there's something called star args and star. And actually, let me pull this up because this is a really useful Python concept. But it's useful when you want to be able to pass, like a list or dictionary of arguments. So the dictionary uses 2 stars.
Is that a Python for reading, or is that also?
No, that's in Python too as well. Yeah. Let's see.
Args and quarks.
Yeah, and this can be useful if you kind of have a bunch of parameters and don't know how many you'll have.
I actually find this really weird and annoying because, in some things, in parts of PyTorch, parts of NumPy, they expect a shape as a tuple, and sometimes they expect the dimensions as arguments. So in this case, the thing that Rachel's using is the dimensions as arguments. So if the star there, because it was expected as a tuple, you wouldn't have a star. They're totally inconsistent.
Okay, so that's true about this issue with shape, but I do want to say star args shows up other places that can be useful.
This is where it appears all the time.
Yeah. Actually, let me show an application I really like of star.
I didn't have this star.
Okay, yeah. I'm going to be careful about that.
Okay. So we're going to stop here today since I do have a mild headache and I really can't download anything else into my brain. But we'll pick up in this same notebook tomorrow with just reviewing the content and then trying to apply the content at a later date. So, all right. Thanks for tuning in.